Okay, thank you again for inviting me. I'll just give you a short talk about some activities that I've been involved in with students and some partners working on monitoring primarily rooftops. And what kind of led me to this line of research, my background is in doing research on all aspects of urban water systems. And this growth in Internet of Things that's kind of illustrated in this animation uh, really motivated me to think about how Internet of Things can be applied, in particular to stormwater infrastructure. And stormwater infrastructure has evolved over the past couple of decades, where we're not really thinking about large centralized solutions such as stormwater management ponds that have been built over the past decades, but we're moving more towards small scale distributed uh, blue and green infrastructure. And part of this infrastructure are things like blue roofs, or roofs that hold water and then release it when we want them to release rather than instantaneously, and green roofs, which come in different varieties. But one of those is the facility that we have on campus called the Toronto Metropolitan University Rooftop Living Lab. And this is basically a rooftop farm. And rooftop farms are relatively new development. So what struck me is that we could perhaps merge this growth of Internet of Things with the growth of small green infrastructure so that we can gain some insight and into their functioning, and also develop some solutions that would facilitate long-term monitoring for performance and maintenance purposes. So amongst these different technologies, that one of the things that's driving Internet of Things is the miniaturization and decrease in cost in devices that can be used to monitor things, right? A lot of this development has been in the area of consumer products. So we have everything from smart microwaves and fridges, and our cell phones, and a variety of consumer smart devices. But one particular development that occurred in kind of the period that I was showing on the previous graph since 2019 is this technology called LoRaWAN, or Long Range Wireless Access Networks, as well as other low power technologies that basically have some functionality that is very amenable to implementation in monitoring green infrastructure. So some of these strengths are that they're low power. They can transmit small pieces of information, such as sensor readings over very long distances on that low power. And the image on the right shows the transmission from something called the Things Network, which I'll talk about in a minute, that we were using that was able to transmit on milliwatts of power a signal from a balloon, in this case, to a distance of 830 kilometers away. But in generally, the range is in kilometers. The range of this technology is measured in kilometers with very low power. What's also attractive is that it operates in license-free spectrum worldwide, so there are no licensing costs associated with it. It facilitates geolocation, end-to-end security, and over the last 5 years, a growing ecosystem of hardware and software has been developing. So these images on the bottom right are just showing some of the devices that are now out on the market that are relatively low cost, and again have this benefit of being able to collect sensor data and transmit it over long distances at a very low cost and very low power. So in 2021, 22, we basically purchased some of these devices and we deployed them on the rooftop farm. So this is the picture of the rooftop farm early in the season. And these are basically off-the-shelf products that required a little bit of wiring and a little bit of programming. And what we were interested in is monitoring the runoff from the roof. So here we have a level sensor that's connected to a node that is transmitting this data from the sensor. So we were monitoring rainfall on this roof. We were monitoring the runoff from the roof through these roof drains. And this little sensor tree is showing two temperature and humidity sensors, because we know that green roofs contribute to have some cooling effects on microclimate. So we wanted to quantify that at this rooftop farm. The basic setup is that we have sensors connected to a device that connects to a gateway, and all this information is being fed to the cloud, and then we can show it in. I'm just showing UV dots as one of the platforms that are either low or no cost that allows you to visualize that data. So at the end of 2 monitoring seasons, we were able, with these low-cost devices, first to capture all the data. I mean, we didn't have a lot of lost data. Less than 1% of the data wasn't transmitted. But we were able to quantify the hydrologic performance. So we can see basically the effects of harvest, something that you normally don't see on conventional green roofs, where typically extensive green roofs contain low sedum plants and that don't change really over the spring and summer season. And we were able to quantify the hydrologic performance in terms of the retention of the water, the attenuation of the peak flows, and the delay in these peaks, which are all important in managing stormwater collection and stormwater management systems, where we're trying to promote the natural water cycle and delay and retain as much water as possible, rather than simply conveying the stormwater from roofs. Yes?
You're at 9 minutes.
Okay. We also, using temperature and humidity sensors, we were basically quantifying the thermal benefits of using different plants. And there's more than 20 varieties that are grown on this roof. What we're doing now, and the project we started this year in collaboration with Credit Valley Conservation, is utilizing a smart blue roof. And I don't have the time to explain it, but I put a link here to a very good overview of the smart blue roof given by Credit Valley Conservation at a conference last year. And it's this building A that basically has valves to control the runoff from the roof. And we're working on quantifying also the thermal benefits of this, using the same sensors that we moved from our rooftop farm. And then we're going to be modeling using the data collected from this building to see what benefits could be realized on a street scale and on a neighborhood scale. And just a note on monitoring these devices. I mentioned earlier an organization called the Things Network, which basically provides a free backend for all the data. So once you register a sensor node, all the backend or the collection of the data and storage and is in the cloud is basically provided for free. So we were using this on our rooftop farm, and this year we added another network that is not free, but it's very low cost, called Helium, that has, I think, close to 1 million hotspots across the world. And across Southern Ontario, we have basically coverage of all urban areas. And the cost of using this network for 100 devices communicating once per hour works out to about $8 per year. So it's next to no cost.
Thank you, Darko.
This is just a list of publications that we have, a list of papers we've published on this topic over the last couple of years.
I'm from Eco Innovation Lab. Eco Innovation Lab was formed several years ago as a digital transformation partner, bringing together industry, academia, and government together, specifically for digital solutions within the built environment space. We do a number of different lines of business within Eco. I want to talk about the collaborative R&D side of things. One of our flagship projects was One Ontario. Some of you may have heard of it. It was endorsed by about 40 agencies in Ontario, trying to unify the information exchange as it relates to development application process. So building new housing, building permits, develop application permits. The idea was to create a data exchange standard between all the different parties that are involved in that effort. It was funded by CMHC, and we made some really good inroads. Another related project was we've partnered with 6 universities. York University has been added to this recently. It just hasn't been updated. It's a 5-year My Tax Cluster project, over 1.3 million, and with the goal of AI-enabled digital twins, specifically for automation within the regulatory systems in the built environment. So I'm going to talk about what that means in a minute. But the initiative I want to talk about today is data, and how data needs to be gathered from all these different sources in support of development approvals specifically. So the data platform that we put together is called LandLogic. It collects and compiles and digitizes data from different sources related to land development. So as many of us know, urban data is siloed, unstructured, and scattered. That means access to information is very difficult for a number of different reasons. Land data resides in different jurisdictions, so municipalities, conservation authorities, upper tier governments, so on and so forth. It's in different formats depending on the jurisdiction. And the solution that we kind of put together was a data fusion engine that standardizes geospatial data across jurisdictions into one database. Once that's done, you can then query that data, and it has a number of applications, from analyzing potential land value to enhancing transparency on the development approval process, and also informing policy when it comes to anything affecting land and development. From a digital twin perspective, the data that we put together is at the GIS layer. So we've kind of tapped into open data that's available across different jurisdictions, but we've also now digitized data that wasn't digitally available. So open data like zoning, that's not in a digital format. We've kind of digitized that as well and compiled that in our GIS infrastructure. And the next steps is to bring in the building information model into it. So once the building information model comes onto the GIS infrastructure, then we can talk about a lot of digital twin applications that Darko as well as Steve kind of hinted to earlier in this presentation. So that's really where our head is at in terms of infrastructure. But talking about what does it mean in the regulatory context, the GIS data that's available at the regulatory context is basically anything that has to do with land use planning, so official plan, secondary plan, so on and so forth, zoning designations, all the environmental and protection constraints, conservation authorities, floodplains, wetlands, so on and so forth, heritage designations, and then obviously the asset and infrastructure location. So where is the servicing for different different parcels of land, and so on and so forth. So that's what the GIS infrastructure brings to the table. On the BIM side, obviously that's the information about the building. So there's a lot of assets that exist in a BIM environment that could be used for regulatory checks. So automated code compliance is a good example of it. Why BIM? I want to kind of put this slide in here. BIM may be foreign to a few of us on this call, but started in the design world and the traditional workflow, the design, construction, and regulatory. There's a lot of loss of information. With the BIM workflows, design and construction teams are now working together so that knowledge loss doesn't happen. But as soon as we submit something for a permit to a municipality or jurisdiction, then it's PDFs again, and in many cases it's still paper. So that is a huge information loss that happens from design and construction onto regulatory, and pushing that BIM workflow into the regulatory space would allow the regulatory entities to actually take advantage of all that information that's been gathered by the design and construction team. So that's the reason why we should care about this. As the information comes in, we can check a lot of the building code constraints directly on the BIM model before it even hits the municipality, so streamline development. And of course, combining BIM and GIS together, that's basically the whole game in terms of what can be achieved. Not just building code, but also all the planning constraints, zoning, and so on and so forth can be checked in a BIM GIS environment. As an example of, for example, a particular building exceeding the allowable height. In that particular scenario, there's a lot of 3D analysis that can be done with that, but that's basically where the applications of digital twin in the regulatory environment look like. Other BIM GIS checks that can be done is noise impacts, shadow analysis, 3D shadow analysis versus 2D shadow analysis, view corridors, it's a constraint in some jurisdictions, wind analysis, and so on and so forth. So there's a lot of applications that can be explored in a BIM GIS environment, but that requires that GIS infrastructure, cross-jurisdictional GIS infrastructure to be in place, that you can then bring the BIM asset into it and then assess it against all the requirements that exist. On beyond regulatory, there is other applications for municipalities and government agencies. There's a lot of capital projects going on. Being able to accept a BIM submission, not just for checking the building code, but also for the operation of the asset. It's a big deal. Unfortunately, a lot of our municipalities don't consider that at the moment. Some more sophisticated owners have kind of, especially in the private sector, have moved towards BIM submission for asset management, but it's just want to kind of highlight this for those on the call that might be interested to look into in future. The applications of digital twins in the regulatory context, there's a long range of applications from city planning to smart city applications, emergency scenarios, development approvals is just one of it. And then, of course, digitized infrastructure is the end goal of that particular stream. Now, the foundation for getting any of this done in any scalable format is to make sure that we are not platform dependent. So being able to be platform agnostic and don't get into any vendor lock-ins. The solution to that is obviously the open data standards that exist both on the GIS side through OpenGIS, OGC, Open Geospatial Consortium, as well as on the BIM side through Building Smart International standards that exist on that front. So adopting these open data exchange standards would allow us to not have any vendor lock-ins, and because the space is moving very quickly, there's a lot of solutions coming into the market every day. So you want to make sure that from an owner perspective or regulatory agency perspective, we comply with open data standards to basically have that security against the investments you're making in this space. With that said, I know I kind of went through it very quickly, but I want to give you an overview of where digital twin applications in the regulated space could exist. Happy to answer any questions afterwards. Thank you.
So yeah, like I mentioned, we are primarily an engineering and survey firm, currently employing some new technology to help us in the field to capture data that would integrate into digital twin and BIM models that were previously discussed by Arash and Darko. So in our industry, we're typically doing survey to support engineering projects, civil engineering projects, infrastructure projects. One particular demonstration we gave recently was on the Trimble X7, which is a relatively newer model of 3D laser scanning tool from Trimble that helps us integrate our GNSS and total station survey data into a LiDAR scan, into a LiDAR point cloud that we can then extract information to send to our engineers to help them plan and design their projects. So this particular unit, I'm going to share a data set that we recently collected in the field. This particular model is a relatively short range 3D scanner, about 80 meters in its maximum range, but still capable to georeference to our GNSS data in the field to give us millimeter survey grade accuracy of whatever we're scanning. So as I mentioned, a lot of this data integrates well with BIM models, as this particular terrestrial scanner can go from outdoors to indoors, and we can fully map the dimensions of a building. So yeah, as I mentioned, I'm just going to share a data set that we recently collected. This particular data set was a bridge. So obviously, as surveyors, we go out there, establish our control. In a typical survey of a bridge like this, we would likely be at this for maybe multiple days trying to survey this with traditional methods, but using the 3D terrestrial scanner, we're able to cut that time in the field down to half a day in this case for capturing this particular bridge. So as you can see, we can set, we get quite a dense model of what we're looking at on the ground. We can set this parameters to collect more or less points. This is a pretty dense point cloud for what we were interested in, as it was a bridge and features that we were looking to pull out of it. So in this case, I can isolate just the bridge itself and pull out features that we can then extract to our engineers. For example, our ballast walls, our abutment seats. This particular bridge wasn't a full replacement, but rather they were going to reuse the existing abutment. So a lot of the, in this case, they wanted to measure the distance from the abutment face to abutment face on the other side, capture top of abutment elevations, bearing seats, things like that, deck elevations. So as mentioned, it's a really powerful and efficient tool for turning what would be an entire day or 2 days of survey into a few hours of capturing an extensive point cloud of information where we can extract endless amounts of information. This is just one example of how emerging technologies, specifically in LiDAR and 3D scanners, can integrate with infrastructure projects such as the blue roofs that were discussed previously by Darko. We also use LiDAR drones and traditional survey methods, obviously, for collecting things. So, I mean, for the blue roofs, for example, you might employ a different remote sensing technology to collect your data, but this type of information that you're collecting is very important and integral into creating the digital twin models that you've been hearing about, and I'm sure you'll hear further about. So in our industry, one of our challenges is getting this technology into the hands of young people and people looking to upgrade their job skills. We're finding that we're having a difficult time getting people who are qualified or interested in applying for these types of field positions where you can collect this data. We're hoping to help develop a micro-credential program that allows people the opportunity to get out of school and into careers and into the field much quicker, and learning cutting-edge skills like surveying and data collection for projects like I've just shown you. Okay, well, thanks again for having me. I can take any questions that people might have after the presentations are done.